Okay. In celebration of the Falcon Heavies not exploding, the governing equation for rocketry is the sum of the forces thought of as vectors is the mass times the acceleration vector. This is the first and dumbest level at which you start to talk about launching rockets. After you do a little consideration with this, you will discover things like the rocket equation. What was the summary of the rocket equation?
That was you need to have enough fuel to get the fuel up to fuel.
Getting more fuel up.
Yes.
Yeah, so if here's your little ball that you want to get away from and your rocket is up here, right? In order for your rocket to continue to leave, you need to burn fuel up there, right? But to burn that fuel up there, you have to get it there, right? Which means that you have to burn not only the fuel that's there, but fuel down here to lift that fuel up there, which seems like it would really quickly amount to you can't fly rockets at all, right?
Yeah, but you need less fuel up there than you have on the surface.
Yeah, there's some calculations you can do to figure out how much fuel you have to burn to lift a little fuel up there, and thankfully it is less fuel than infinity, basically. So I encourage you to go look up the rocket equation. Spend a second deriving it. It's not impossible. The reason I'm bringing this up in differential equations class is I want you to be able to do the simple one-dimensional version of this. Or maybe even just recognize that this thing's actually a differential equation.
Oh, yeah, acceleration is the second derivative of position.
Good, perfect. Acceleration is the second derivative of position, right? Okay, so if I want to think, okay, here I am, world thing. This thing could certainly be a rocket. It could also be something that you dropped. It could also be something you threw into the air. But they all work this exact same way as long as they're not being fueled currently. Right, so as long as you're not currently burning fuel, there's only one force acting on this object. What force is that?
Gravity.
Yeah, gravity. Right? Okay, so in the case of no thrust. How about that? No thrust. In the no thrust case, you only have one force. That force is gravity, right? What's the force due to gravity on an object? 9.8 meters per second squared.
At the surface of the Earth.
Yes.
Mostly, sort of.
Well, in order to get the force, you need to multiply it by the mass of the object that's being affected by it.
Uh-huh. Right? So the one and only force is mg. Right?
One down.
And then, no, this is chill. And this points downwards, right? Okay, so adjust your coordinate system to point downwards. And what this is, right? This is, oh, Mania's pointing out something. What was Mania pointing out?
That the value of G is going to change, you know, as you get further away or
Yeah.
closer to
You guys with that?
the Earth.
The value of G depends on your position above the Earth, right? So I have something like this, right? M times G of P is what? What was the other side?
The force on that thing.
Right, this is the sum of the forces. So I've got the one and only force acting on my rocket is, or on my dropped object, whatever, is mass times the acceleration, and you said acceleration is the second derivative of position, right? all with me on this? Okay, so what's this thing? Well, one, you can slash the m's out of there, right? You guys see that? Really, all you have is p double prime is some function of p. You guys cool with this? In the dumbest possible case, where you're near sea level and rounding badly, right? So if you're near the ground and rounding, what does this equation become? Yeah, p double prime is a constant, right? Specifically in the usual unit system, minus 9.8 meters per second per second. You guys with this? Okay. How do you solve that differential equation?
Integrate twice, it's close.
Yeah, just integrate twice, right? Okay, so let's integrate once. So we're gonna integrate p double prime dt is gonna be the integral of minus 9.8 dt. And so we'll get what? P prime is 9.8 t, oops, minus 9.8 t plus some constant.
Which turns out to be your initial position.
Close. If you plug 0 into this, right, you should get p prime at time 0. P prime is velocity. So you got velocity at time 0, that'll be your constant here. Cool. And then you integrate again, right? So you get p of t, right, is
4.9 t squared.
yeah, so minus 9.8 over 2 t squared plus v naught t plus p naught. You guys with this? Okay, the use other than rocketry that this has is figuring out how tall cliffs are. Which, trust me, is occasionally a life or death thing for me. Because when you're standing at the top of a cliff with a 200-foot piece of rope, you would really like to know if it's going to reach the ground.
So you can't just lower it down and see if there's something.
Sure, you can, as long as it's not dark or raining or tree. It happens, man. Sometimes it's windy, there's trees all over the cliff, you throw your rope and it goes thump into a tree. Then you pull it up and you try to throw it again and it gets blown into a tree. Right? And so you would like to know, like, is this thing 200 feet tall or not?
We did that problem in the first physics class.
Yeah, this should be a like beginning physics problem. So what you do is you take a rock and you shout, rock. Don't be a jackass and drop rocks off cliffs without shouting things. Look very carefully for people. Try to follow them if you can. I mean,
Well, I'm not counting, but.
and then drop your rock and count. Right? What's the initial velocity that I'm giving to that rock? 0, right? So in the case of rocks, dropped rocks, yeah, and you can throw it straight out. You guys see that? Like if you throw it straight out, it's got some velocity, right? But that velocity isn't in the gravity direction.
Only the x direction.
Right? So that's this whole, you might want to think about it in vector land.
I guess no z direction.
So if you drop your rock, you're really looking at P of t is, and we're going to count, so we're rounding badly. So we're going to do minus 5 t squared plus p naught, right? Okay. So what? If you want to figure out how tall the cliff is, you drop your rock, what do?
You You're gonna count the time, plug it in.
Count the time, wait for it to hit, right? When it hits, what's the position? Yeah, you think about that as being 0, right? You guys see that? So P of the special T where it hits, right? Like if your hit is at T naught, right? Some value that you counted, 3 seconds or something. Then you've got 0 equals minus 5 T naught squared plus P naught, right? P naught's what you're looking for. T naught's the thing you know. So what do you end up doing here?
Probably just solve for P naught.
Yeah, solve for P naught. Square and multiply by 5. Right, so if you drop your rock and it takes 4 seconds to hit the ground, square 4, which is 16, and then multiply by 5, which is 80, which is in meters, which means that your 200-foot rope will not do it. 200 feet is 60.
Yes, 6.
Cool. So where's the breaking point? Will 3 seconds do it?
Yeah, that's fine.
3 squared is 9, times 5 is 45, right? 3 is fine, 4 is not. If it takes much longer than 3 seconds, it's a bad idea to do it, right? I kid you not, if I had $1 for every time I had to do this, I would have at least one more rope than I have.
Wow.
Like, it definitely happens that you'll like get to the top of something and your headlamp is of course dying and of course it's raining and you're like, I don't know if this is the right way to go or not. Rock, drop, 1, 2, 3, 5. Fuck this. Let's go for a walk and find something else.
That's when you jump on the tree and then that momentum.
Cool. So this equation, right? The kind of the take home of this lecture should be this differential equation that we got by being near the ground and rounding badly. But we could solve this other more general differential equation, right? If we knew how gravity worked, we could figure out even what that function is. You guys see that? If we spent a minute playing with big chunks of lead, we could maybe calculate how gravity works, or at least approximate how gravity works. We still wouldn't understand why gravity works, but we would know how it works. Those are different things. Cool? Questions, things? We should all be amazed that the Falcon Heavy didn't blow up, by the way. Because that has not just this little tiny differential equation in it, but probably a couple hundred differential equations.
Has that trick ever failed you?
No. Because it turns out that math works.
Does
It's those like 3 foot. Yeah, so I do this trick assuming that I have a 60-meter rope and I actually carry a 70-meter rope. So yeah, it usually works. I have never ended up in a position that was really, really bad by using this trick. I have ended up a couple of times in a small tree.
Yeah, like a couple of feet off the ground.
Yeah, and you can drop a couple of feet. That's not such a big deal. It's the like, oh, I rappelled into a little bush, or I heard the rock hit a ledge, and so there's this ledge that's a little ways off the ground, and I'm standing next to a small tree, and I'm like, do I use this little tree to get the rest of the 15 feet to the ground, or what? Like, that does happen.
Carry a rock with you on the way down so you can see how far you are from there.
Well, once you start going, once you're halfway down.
Yeah, once you're halfway down, you're kind of committed to like being that far or further down. There are ways to go back up a rope, but they really suck.
Especially in the